Then back to the original current. They now replace the coil with another one, with more turns in the wire.
More nails are picked up. What happens when you turn off the voltage?
Falls off as well.
Okay.
So you need to know that electromagnets are temporary and their magnetic fields can be turned on and off. The strength of an electromagnet can be increased in 3 ways. By increasing the size of the current and by making more turns in the wire, we will increase the magnetic field. And by adding a soft iron core inside the coil, we will also concentrate the magnetic effect. Knowing that electromagnets can be turned on and off makes them very useful, and they're used in a large number of different appliances. They make loudspeakers vibrate and motors go round, and they create recordings onto audio tapes, computer discs and videotapes. They're also used in relays. This is a switch where a small electric current will switch on a much larger current, and relays are often used for safety reasons. Electromagnets are also used in electric bells. When the current is turned on, the electromagnet attracts the hammer, which clangs the bell but also breaks the circuit. This then turns off the electromagnet, which releases the hammer. The arm springs back to its original position, making the circuit complete again. And so it goes on very quickly, as we can hear. So let's look at a question from a test paper about electromagnets. This is a diagram showing an electromagnet used in a door lock. We can see the push switch, the electromagnet in the door frame, the iron bolt in a spring and a section of the door. So the question is, if the push switch is closed and the door unlocks, explain in detail how this happens. 3 marks have been awarded for this answer, so we're probably looking for 3 points. So what is the sequence of events from when the switch is closed to the door unlocking? Well, the switch makes the circuit complete and a current flows. The iron core in the coil will become magnetized, producing a magnetic field. The iron bolt is then attracted to the electromagnet and springs out of the door frame, unlocking the door. The examiner will also be looking to make sure you have got the order of events correct. So remember, when the switch is on, first of all, a current flows, which magnetizes the iron core, which then attracts the iron bolt. This brings us to the end of electromagnets. If you weren't sure of the answer to the question, why not go through this section again? Here are some more top tips to help you with your revision.
For revising my physics, I used a lot of flashcards and I even had my little brother help me.
I revise for about 20 minutes at a time and then I have a break so I can keep my concentration better.
When you're revising, do try and stay fresh, and you can do that best by making sure you do different things. Don't concentrate on one thing for too long at any one time. So, for example, you can make yourself revision cards, you can read your notes, you can try test papers, you can get somebody to test you. Whatever you do, vary it.
Our last physics unit is about the conservation of energy. First, energy transfer and storage. In Programme 2, we looked at different types of energy, but let's just remind ourselves of the 7 different forms. Light energy from anything luminous like the sun, light bulbs or candles. Electric energy whenever there's an electric current flowing. The hotter something is, the more thermal heat energy it has. There's sound energy from anything that makes a noise, vocal cords, speakers, noisy machinery. Chemical energy is energy stored chemically, which can then be released. Food, fuel and batteries all have stored chemical energy. Potential energy is stored energy that's ready to be released. For instance, high skydivers about to leave an aeroplane. And finally, kinetic energy is the energy of any moving object. Now, the tricky bit is that energy can not only be stored, but can also be transferred from one form into another. Watch this next clip and make a note of some of the energy transfers you can spot.
This kettle needs energy to boil the water. And it's energy that makes this radio work, or it will when I wind it up. I'm not creating the energy, I'm transferring it from my muscles to the spring, where it's stored until it's needed. Energy transfers are responsible for just about everything in the universe, and they're not difficult to spot. The energy that was stored in the wood is being released by burning and gives off heat and light, and if you listen, sound as well.
No signal in here. Tried outside. Another energy transfer. But where did the energy come from for my muscles? It's been through quite a few transfers to get to me.
The energy was transferred to me through my breakfast. The energy was stored in this food. When I ate it, some of it went into keeping me alive and warm. The rest was stored for when I needed it. But where did the plants get their energy from?
The sun is the main source of energy used on Earth. Now, plants capture their energy from the sun by photosynthesis, which involves green plants turning light, carbon dioxide and water into food, which is their stored energy. So all along the way from the sun to me, energy is being stored and released. Now, food is an energy store, and any stored energy is called potential energy. So, when the energy from food is released,
is transferred into thermal, kinetic and potential energy. Light energy from the sun is transferred into chemical energy and potential energy stored in the plants. When Stella winds the spring up, kinetic energy from the moving arm is transferred into potential energy stored in the spring. When the spring in the radio is released, the potential energy is transferred into kinetic, electric, sound and thermal energy. Lots of examples of energy transfers.
This is the radio from the plane. I've built a machine to try and make it work.
now what energy transfers are going on here?
The bucket fills with water. High up, it has potential energy. When it's heavy enough, it starts to fall. As it comes down, the potential energy transfers to movement or kinetic energy in the wheel. As the wheel turns, kinetic energy is transferred to this dynamo. It also produces sound and a bit of heat too. The dynamo transfers kinetic energy into electricity. And the radio transfers the electricity to sound and some heat.
So the whole system is mainly a transfer of potential energy and kinetic energy. Now, only 6% of the potential energy the bucket had is going to the radio. So it's not very efficient, but it's very useful.
So we know that energy can be transferred from one form to another. But as we saw in the clip, only 6% of the energy from the bucket went into the radio. So Stella's system wasn't very efficient. What happened to the other 94%? Well, one of the key points about energy you need to understand well is that energy never disappears. It's never destroyed. It's always transferred from one form into another. And in the case of Stella's invention, the energy that didn't pass into the radio would have been wasted energy in the form of thermal energy and sound energy. No energy is ever destroyed. This is what we call the principle of conservation of energy. Energy can never be created nor destroyed. It's transferred from one form into another. Another important fact about energy is that it's often only useful when it can be transferred from one form into another. When you think about it, all useful machines use one kind of energy and give out another. For instance, this light bulb converts electric energy into light energy so we can see by it. This radio transfers the chemical energy stored in the batteries into sound energy. And this kettle converts electric energy into heat energy, which is what we need to boil the water. One form of energy transferred into another useful form. These are really important key points to get to grips with. First of all, the principle of conservation of energy, which you need to learn. It states that energy can never be created nor destroyed, but is transferred from one form into another. So energy is never lost completely, but it can be wasted and become something less useful, like thermal energy or sound. And remember, energy can be made more useful when it's converted from one form to another. Here's a question about energy transfers from a past paper. It's about a bell in a church tower that's attached to a wheel and balanced upside down. From the edge of the wheel is a rope that the bell ringer can pull to set the bell ringing. The energy given out by the bell was originally stored in the bell ringer. So the question is, describe the main sequence of useful energy transfers which take place when the bell ringer rings the church bell. Now, 3 marks are on offer for this answer, so you're looking for 3 energy transfers. Stop the tape and have a go. So, what's going to happen? The bell will start moving and then fall the rest of the way round and make a sound. But that's just describing what happens and won't get any marks. The question wants to know about the energy transfers that are taking place. So let's have a closer look. So first, chemical energy stored in the bell ringer's muscles is transferred through the rope to become kinetic energy in the bell. As the bell begins to swing, kinetic energy changes to potential energy. And finally, the potential energy in the swinging bell is transferred into sound energy in the metal and the air. It's quite complicated, so you may want to go through the question and answer again. If you feel happy, you can move on to the next section on temperature and thermal energy. First of all, let's sort out what we mean by temperature and heat. For a start, they represent different things. Temperature is a measurement used to measure how hot something is, and its unit is degrees. Heat is a form of energy, often called thermal energy, and we measure it in joules. The trouble is that we commonly use the word temperature in the wrong way. For instance, when we're ill or feverish, we say we have a temperature, when what we really mean is that the temperature when we are ill is higher than our normal measure of temperature. Let's take a closer look.
Temperature is measured in degrees, and the scale we use mostly nowadays was worked out by a Swedish astronomer called Celsius. Now, a thermometer would be useful for me to check that the cave isn't too cold for my plants. But this one hasn't got a scale. Probably could make one. The bulb is surrounded by melting ice, and the ethanol has had time to settle down. It stopped moving. The ethanol is dyed blue so we can see it. Ice is frozen water. And this mark indicates the freezing point of water, which Celsius called 0 degrees.
Heating the ice will turn it to water. The energy in the water is being transferred into the ethanol, so it raises its temperature. The heated ethanol moves up the tube because it's expanding.
The water is now boiling, and the ethanol has stopped rising. This mark is the boiling point of water, which Celsius called 100 degrees. Now, by dividing the distance equally between the 2 points, we get a scale. And the level of the ethanol will tell us the temperature of whatever's surrounding it. So, if I leave this here, it will tell me the temperature of the cave.
So temperature and thermal energy, heat, are not the same thing. This sparkler is extremely hot, and if I touched it, I would get burnt. This basin, full of warm water, is at a much lower temperature than the sparkler. I can put my hand into it. But which do you think has the greatest heat energy? In fact, although the water is at a lower temperature, it contains more thermal energy. This is because there are far more particles moving about in the body of water than at the tip of the sparkler. The atoms in the sparkler are vibrating a lot, but there are far fewer of them, so the total energy is much smaller than in the basin of warm water. So you need to know that temperature and heat are different. Temperature is a measure of how hot something is, and we measure temperature in degrees Celsius. Heat is thermal energy, and it's measured in joules. We're now going to look at what happens when there are differences in temperature. Thermal energy is only transferred if there's a temperature difference between two places, and the heat always travels from a hotter to a colder place. This can happen in three different ways, called conduction, convection, and radiation. Let's look at conduction first.
This metal bar is covered in a special material that changes colour when it gets hot. The energy is transferred from the water to the bottom of the bar, so it gets hotter. And the changing colours show the energy transferring along the metal. But what is actually happening?
Particles in a solid are vibrating all the time. How much depends on how hot they are. More energy means more vibration. The metal bar is heated at the bottom, and the energy moves from one particle to the next, making each in turn vibrate faster. The energy always moves from hot areas to cooler ones.
Conduction is when vibrating particles pass on their extra vibrational energy to neighbouring particles. That's why a metal cup full of hot water feels too hot to hold. The thermal energy from the hot water is conducted through the metal to my hand. But this polystyrene cup is safe to pick up. The thermal energy isn't conducted through the material from the hot water to my hands. Metals are good conductors, while the polystyrene is a poor conductor, but a good insulator. The second way thermal energy travels from hot things to cold things is called convection. This is where heated material moves in bulk to a cooler region and takes the heat with it. For example, this is how radiators heat up a room. The air above a radiator warms up first and rises to colder parts of the room. Colder air replaces the warmer air and again rises, so a convection current is created. The third way thermal energy moves from hot areas to cold is by radiation. All hot objects radiate heat to their surroundings by invisible waves. Unlike convection and conduction, these waves don't need particles of matter to travel through. This means that energy waves can pass through a vacuum, and that's how the sun's rays reach the Earth. A thermogram is a special camera that is sensitive to thermal energy, and here we have Femi demonstrating.
You can see it on my face. It's different colours depending on how warm various bits of my face are.
My eyes are hottest, my nose is cooler, and my green hair coolest of all.
First of all, thermal energy is only transferred if there is a temperature difference, and heat can be transferred in three different ways. Conduction is when vibrating particles bump into other particles and pass on their energy. Convection is when a hotter region, such as water or air, moves in bulk to a cooler region, taking the heat with it. And finally, radiation. Here, hot objects radiate thermal energy to their surroundings by invisible energy waves that do not need particles of matter to travel through. Brilliant! You have come to the end of this third science programme in the Key Stage 3 Bitesize revision series. Don't forget that to complete all your revision, you should look at programmes 1 and 2 as well. Remember always to plan your revision time well ahead and give yourself plenty of breaks. And don't forget the book and our own unique online website that go with these programmes. Whatever you do, remember, it's your choice.
Want a lesson plan? You can do it in your sleep.
With easy peasy lemon squeezy.
This lush environment has an unmistakable smell.
You're the boss, okay?
Oh no, not more children! Schools on BBC Learning Zone. What every smart teacher dreams about. Every night throughout the week on BBC Two.
For a copy of the current BBC Learning Zone programme guide, send an A4 stamped addressed envelope with stamps to the value of 33p to BBC Learning Zone,